Welcome back to our study of the fundamentals of operating systems based upon the textbook Operating System Concepts, 10th edition, by Abraham Silbershatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. In the last unit, we were introduced to the memory management system of the operating system. And in that unit, we concentrated on the early forms of memory management that required that the entire program be loaded into memory before it could run. We talked about contiguous memory allocation, and we talked about partitions, and then we were introduced to the concept of paging, where the memory is divided into equal-sized blocks called frames, and the program is divided into equal-sized logical blocks called pages loaded into frames. However, all the pages of a job still had to be loaded into memory in order to run. Now, we were introduced to the concept of swapping, where pages could be swapped in and out of memory. In other words, they could be written back to the secondary storage and then brought back into primary storage, but that still did not eliminate the need for them all to be in memory when the job was running. That simply allowed the operating system to move some pages of an inactive job that did not have the CPU back to disk and bring in more pages for another job that did have the CPU. Now, in this unit, we're going to start discussing the modern approach to memory management that operating systems employ, and that is referred to generally as virtual memory. And in this case, the job does not have to be entirely in memory in order to run. So why don't we start talking about how this works? As I've already said, in the last unit, we discussed some of the early forms of memory allocation used in computer processing, and all of those require that the entire program be in memory before running. That requirement amounts to a severe handicap as programs continue to become more sophisticated and subsequently much larger. Now we will move on to a memory management scheme that allows the system to load only enough of the program it needs to proceed and bring in other parts as they are called for. This scheme is referred to as virtual memory, since the approach makes it appear to the user that the entire program is loaded and running. With this approach, programs can be larger than physical memory. Virtual memory abstracts main memory into an extremely large, uniform array of storage, separating logical memory as viewed by the programmer from the physical memory. This technique eases the concern of enough memory availability for programmers. Virtual memory also allows processes to share files and to implement shared memory. However, virtual memory is hard to implement and may substantially decrease performance if it's used carelessly. We'll attempt to accomplish the following objectives in this unit: to define what virtual memory is and describe its benefits, to illustrate how the pages are loaded into memory using demand paging, to apply first in, first out, optimal, and least recently used page replacement algorithms, and describe the working set of a process and explain how it is related to program locality. The number one requirement related to memory that we have learned is that the instructions being executed must be in physical memory. We've got that down pat. In fact, we spent quite a bit of time dealing with the requirement to place the entire logical address space in physical memory. Dynamic linking is helpful, but still burdensome on the programmer. At first glance, the requirement that the instructions must be in physical memory to be executed makes sense, but on the downside, it limits the size of a program to the size of physical memory. The fact is that in many cases, the entire program is not needed. For example, code that handles unusual error conditions does not have to be in memory unless one of those unusual errors occurs. Also, arrays and lists and tables are often allocated more memory than they really need. Also, some features of a program may rarely even be used. So why do we have to load the entire thing in memory if it's not being used? The ability to execute a program that is only partially in memory would be very beneficial. The fact that a program would no longer be constrained by the amount of physical memory that is available is a great benefit. Users would be able to write programs for an extremely large virtual address space, simplifying the programming tasks. Because each program could take less physical memory, more programs could be run at the same time, which would increase CPU utilization and throughput, but without increasing response time and turnaround time. Didn't we agree that these are all major goals of an operating system? Increasing CPU utilization and throughput, reducing response time and turnaround time? Less input-output would be needed to load and swap portions of program into memory, so each program would run faster. So as we can see, running a program that is not entirely in memory would benefit both the system and its users. Virtual memory involves the separation of logical memory as perceived by developers from physical memory provided by the computer. This separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available, as you can see in this slide. Surely you remember our discussion in the last unit how address resolution converts that logical and memory address space into physical memory address spaces. As you can see in this slide, the logical address space is much larger than the physical address space. The virtual address space of a process refers to the logical or virtual view of how a process is stored in memory. Typically, this view is that a process begins at a certain logical address, say address 0, and exists in contiguous memory as shown here. Recall that in the last unit, though, that in fact physical memory is organized into page frames and that the physical page frames assigned to a process may not be contiguous. It's up to that hardware utility, the memory management unit, to map logical pages to physical page frames in memory. Notice in the figure on the right that we allow the heap to grow upward in memory as it is used for dynamic memory allocation. In computer science, a heap is a specialized tree-based data structure. The heap is one maximally efficient implementation of an abstract data type called a priority queue that we talked about earlier. In fact, priority queues are often referred to as heaps regardless of how they're implemented. In a heap, the highest or lowest priority element is always stored at the root. A heap is a useful data structure when it is necessary to repeatedly remove the object with the higher or lowest priority. Similarly, we allow for the stack to grow downward in memory through successive function calls. The large blank space between the heap and the stack is part of the virtual memory address space, but will require actual physical pages only if the heap or stack grows. Virtual address spaces that include vacant blocks like these are known as sparse address spaces. Using a sparse address space is beneficial because the vacant blocks can be filled as the stack or heap segments grow, or if we want to dynamically link libraries or some other shared objects during the program execution. In addition to separating logical memory from physical memory, virtual memory allows files and memory to be shared by two or more processes through page sharing. We talked about the issues of processes sharing pages in the last unit. Doing so leads to the following benefits. System libraries, such as the standard C library, can be shared by several processes through mapping of the shared object in the virtual address space. Although each process considers the libraries to be part of its own address space, the actual pages where the libraries reside in physical memory are shared by all the processes, as you can see here. Typically, a library is mapped read-only using that protection bit that we talked about in the last unit into the space of each process that is linked with it. We've already discovered that two or more processes could communicate through shared memory rather than message passing. Virtual memory allows one process to create a region of memory that it can share with another processes. Processes share in this region consider it part of their own virtual address space, yet the actual physical pages of memory are shared, much like we see in this image. Well, that's a good introduction to our topic. Why don't we take a break now, update our study guide, and when you're ready, come on back for lesson 2 on virtual memory.